So who knows what formal verification is about? Okay. Who knows what model checking is? Wonderful. So, and then I will simply go over it relatively quickly, and once again simply present you the way I'm doing it, my group is doing it. So, let's start with this. It's a little dark, but I guess you can get an idea. This some picture with different colors. What do you think it is? Some what? It's a tree, some source file. What other options we had?
Functions, variables, a program in some language.
Program, but why is it looking like a graph, like a tree?
Execution path.
So that's exactly the case. This is a model, right, which represents the functionality of some program. In fact, it's not a random tree. This has been generated by a simulation tool called Hugo, and it models 2 trains in 1 bridge. So there is some embedded software controlling trains, which supposedly have to go over a single track on a bridge. And they're supposed to coordinate their efforts while crossing the, going across the bridge. So that shows you, in fact, really a very simple program, but there are many opportunities how the trains could behave while crossing the bridge. So, and why do you think I'm showing you such a thing?
Just to illustrate the complexity of this simple task.
Yeah, exactly. Very good answer. It's exactly what I'm doing. I'm showing you that in order to understand the all possible interleaving between 2 trains over the single bridge, I have to explore so many possibilities of this interleaving. And it quite easily becomes a non-trivial task. So many opportunities to check, right? And it's what formal verification is about. We formally, using mathematical methods, are verifying if there is anything wrong going on in the embedded software. So the area I'm working on, which is called model checking and theorem proving, is about modeling systems and then examining these models for all possible interleavings, for all possible coordination among the pieces of the system, trying to find any particular violation or absence of any violations. So it's a very complex task because it requires a lot of graph traversal. In a nutshell, it's about graph traversal. It's about creating graphs and then searching these graphs. So there is a lot of relation to graph theory, there is a lot of relation to system modeling and logic. So because I need to have formal proofs showing me that system is correct. It's what I'm going to do in the first part of my lectures, just to explain you how exactly it could be done formally, and then I will focus on a particular examples which demonstrate my area of research. Okay, so starting from the very beginning. So my motivation is to try to verify any piece of software, any hardware design. And as time goes, our computer systems are becoming more and more complex. So naturally, everybody is trying to test their products, hardware design, so software, and naturally it's becoming more and more difficult. So the systems are way too complex, and testing is not doing a good job any longer. So there are difficulties. So the embedded embedded software has increased functionality. Like 10 years ago, 15 years ago, we would have simple devices and simple control units to control those devices. And these days we have very complicated systems, like, for example, our cars, which these days could be fully automated, and they have embedded computer inside of the automobile and controls just about everything. So it's really non-trivial to make sure the controller, the computer works properly. And as a result, we have more and more dependability concerns. So if you have a fully automated car, most likely we fully depend on the computer. So if the brake does not work, so we do depend on it badly. If the window doesn't open mechanically any longer because it's fully automated, we cannot get out of the car in case of the accident and things like that. So it's really a big concern. And that is indeed the trend, that all devices are becoming dependent on computers completely. So we do need technologies and techniques which would allow us to verify, to ensure that our systems are reliable. So that's the last point I am making, that because of this increased dependability, we have really increased concerns about security and reliability of devices we are relying on. So bugs or program violations, they are unacceptable in many applications, in safety critical and security critical applications, such as medical devices. If you have any operation on your heart and a robot is doing it, and a robot has an embedded controller, computer inside of it, and if it just cuts the wrong part of your body, it's not good, right? So, and the same is about safety critical systems such as space systems, mission control systems, banking software. So, while some errors are still okay to have in small applications, such as, for example, Windows device drivers, right? So in other applications, it's impossible to have bugs. So we don't want to have a bank which loses our money. So we don't want to have banking account which cannot guarantee that it's fully reliable and nobody can transfer your money from one account to another. So in large systems, errors, bugs are quite expensive. So if you have a product already in the market and you are trying to, and you find errors much later when the product already being sold and used by many people, it's very difficult and very expensive to fix these errors. So the intention would be to try to catch the bugs as soon as possible, meaning during the production of your software. So therefore, the technology which we are interested in not only being good in catching bugs, but the technology which would allow us to use this during design of the products. So, and it's very critical that whatever we are doing could be fully automated. So if it requires manual effort, then most likely it will be error prone. So we want something which could be fully automated to avoid it. So here is an example. I really love using it, and some of you already heard this example. So maybe some of you who heard it before can tell me what it is. I'm trying to turn off wireless, and where is the link? Yes. So who knows what went wrong? Actually, it says it, right? It crashed due to uninitialized variable. But who knows the story? I don't know the name of the device, sorry. It was in 1999. This is NASA shuttle. They were supposed to land it on Mars and it disappeared. So what happened?
Bugs caused the crash. Bugs caused the crash. The bug caused the crash.
Right.
It was something in the altimeter.
In what? Okay. No. Oh, yes, exactly. So I'm sorry, I didn't understand your Russian. So, yeah, indeed. But it was a combination of the problems. Essentially, when it approached the planet, Mars, it started getting into vibration mode because the pressure was very different. So because it approached the planet, and because the device started vibrating, the computer, the controller, interpreted it as the device landed on the surface of the planet, and it simply did the right job. It cut off the engines, but it was still above the surface several hundred meters. And because it cut off the engines, it fell, so it crashed. It took some time to NASA engineers to figure out what exactly happened, but the official story is that it was due to uninitialized variable. So it just performed the functionality which was not supposed to be performed. And in fact, they didn't expect it to be happening at all, since it was not tested for this particular execution, for this particular functionality. So they didn't have a technology which we have now, which is called model checking. It allows you exhaustively analyze all possible execution behaviors of your system. And, I'm sorry. I guess I need to turn off not only my wireless. Okay. Well, in 1999 there was no formal verification at NASA. So today it is 2010, and they do have a very large group, actually not one but several, which are working on formal verification, on model checking of NASA applications. So,
well, they have closed the space shuttle program.
So, well, I've heard rumors that they are reopening it. So, but it's indeed true that based on their own problems with very expensive failures, they realized they needed technology which would be able to detect errors like this, because it seems like a very simple problem to detect, right? Like uninitialized variable that could be detected. So yes, NASA now has groups at NASA Ames Research Center, which has their own model checker called Java Pathfinder. So they're verifying Java programs. And then there is a Spin and Jet Propulsion Lab in Pasadena in California. It's where the other model checking tool called Spin is being used to verify NASA applications. And as far as I know, they are doing quite well. So both programs are running well, and they are not going to be terminated. So even despite of all the problems with budgets in the United States. Okay, so here's another thing. I just Googled around and I said security flaws, and it gives me 28 million results. People are complaining about bugs. And you just can start reading it, like vulnerability reports, Windows security flaws, most critical internet security bugs, Skype bugs, and so on. So it just shows how important it is. So then I Googled yet another item, security breach, and it gives me 49 million results, right? So, and it means it just is such an important topic. And like credit agency reports are breached, data at Bank of America compromised, and so on. University of Illinois is hit by security violations. So yes, that's exactly the examples of problems, and that is exactly the set of problems I'm working on, and that's what I'm doing. I'm not doing engineering, I'm not doing lightweight methods. I'm doing hardcore theoretical computer science, but my interest is to make it practical, so this technology would be able to detect problems like this. Okay, so before I start talking about what I do and how I do it, let me just say a little bit about the traditional approaches. So how people find errors in their products? They're testing it. It means they have a product, they have a program, and they run it on some selected inputs, and they observe what the outputs of the system, and they simply compare, is it what I expect my system to do with what it's really doing, and so on. Another approach widely used in hardware design called simulation. So when the model is created to represent the product, the hardware design, and then the model is simulated on some symbolic inputs, and again you simply observe what is the output of such simulation experiment. And then of course there is a classical code review and auditing, completely manual approach, when there is a human being sitting and reading the code and just making intelligent guess if the system is doing the right job. I'm sure some of you are working. Who is doing testing? Who is doing simulation? Who is doing code review and auditing? Who is doing formal verification? Okay, just some of you. Yes. Yes, this is traditional approaches, and this is the approaches which are used by industry. Are they good? They work. Sometimes we say if it's working, it means it's already doing something good for us, right? So, but are they really guaranteeing the results? Are you confident? To some extent, right? So, like Windows product, it's right. To some extent, it's working. Yes, it is. It crashes from time to time. I just restart my system and do it again, right? But you know, is it okay if you do it in a medical equipment? If it crashes from time to time, you don't want it. So there are some applications when that is unacceptable. So there is a huge effort from the research community to push a different technology forward. Of course, it's problematic because, first of all, it's relatively new. There are many gaps. Not everything has been done yet. And furthermore, since it's more thorough and more formal, it's more difficult. It's less practical. It suffers from the problem of being too complex. But at least there is a really effort to make it as simple as possible, as practical as possible, and such that it guarantees the results. So this is exactly my area of research. It's called formal verification by model checking. So those are the problems with existing techniques. And my area of research addresses all of these problems. So let's say testing, simulation, code review, auditing, they're all not exhaustive. It means they test for something, but some behaviors are missed. So in formal verification by model checking, you don't miss anything. So, and I will show you why. Most of the techniques which are traditional, they are not automated, meaning that they do require input from the human, and therefore it's error prone. So again, so the technology which I'm pursuing as my area of research could be fully automated, and I will explain you later why it can be fully automated. So for large systems, these techniques don't scale. So because it just becomes too problematic to review thousands lines of code, millions of lines of code. It's impossible to test a concurrent system, too many non-deterministic interleavings. So technology which I am doing model checking also suffers badly from the fact that systems could be very large. But the advantage of those techniques is that since they could be automated, you can always rely on your tools to try to reduce your system to a much smaller representation. So the classical techniques of testing usually don't guarantee results. Why? Just because they are not based on mathematics. So what can guarantee? If I have a formal proof, if I have a theorem and I prove the theorem, this is the only way to guarantee. So the experience of an engineer who has 50 years of work in a company does not substitute a formal proof. Okay, and these techniques usually cannot do anything about concurrency. So if you have a parallel program, there is so much non-determinism in the execution of individual processes that these techniques would not be able to catch all of them. all possible interleavings. Okay, so the area I'm talking about is again called formal verification. I can represent it as follows. So we build a mathematical model of the system which encapsulates, which represents all possible behaviors of the system. Just like the picture I showed in the very beginning of the lecture. That was the mathematical model. That was a graph representing the train, two trains in a bridge scenario. Once the model is ready, I'm writing a requirement. I'm writing a specification of the system in a formal language, formal specification language, and this specification is independent of the model, but it is about the model behavior. And now, what I'm going to do, I'm going to have an algorithm which will take this specification and compare it with the model, essentially by graph traversal. It will traverse all possible branches of the graph and see if the specification written in a formal specification language is going to be true for all of these branches of the graph. And since this is an algorithm, it means I can implement it. I could have a tool which will do it for me automatically. So the human being is going to be taken out of this picture completely, or not? Where do I need a human?
Where does the coding phase take place?
No, model could be created automatically.
Where does the coding phase take place?
Somebody creates a product. I'm not a programmer. I'm not creating products. I'm only verifying them.
So there is no connection between the running code and the formal method.
To write the verification
What?
to write the verification program.
Verification what?
Program.
Verification, you mean specification of the program?
The specification and the tool to apply. I mean to create the tools that automatically check verify the model.
So I need a tool which performs this task of analysis. And somebody has to create this tool. But it's not a problem. I can verify the tool.
You have to write requirements manually.
Exactly. The only drawback here is that this second bullet, when I'm writing the requirements, that has to be done automatically. Oh, I'm sorry, manually. Somebody has to sit down and write it in a formal specification language using mathematical logic formula, but still it has to be done by a human being. But everything else could be done fully automatically. I can have tools which will create models from a source code or from hardware design description, and I can have tools which automatically implement the graph traversal algorithms. So, which is already really very good compared to other manual approaches. So, right, so so this area is about finding errors in what already exists. So formal is because everything is done using mathematical description. So my model is a mathematical model, my specification is a mathematical logic formula, and verification is essentially a proof. Right? Verification reduces to proving that specification holds or doesn't hold on the model. As I said, it's an algorithm, therefore I can have a tool. Wonderful. The advantage of this technology also in the fact that whenever I'm analyzing, not only I'm proving or disproving, I also can remember the way I'm traversing the graph. It means I can use this memory to remember important things. For example, if I find an error, if there is a bug, I might want to remember how exactly I arrived to the point where the bug exists. So this traversal from the very beginning of the program execution to the violation of my specification is called a counterexample. It shows the trace which I can later use for debugging, for removing the bug. Usually this technology proceeds by exhaustive search of the state space. So my model represents the state space of the system, and I need exhaustive search to analyze all possible state transitions. Yes, it's limited by high computational complexity, but yes, there are techniques which allow us to fight this state space explosion problem. I'm going to show you at the introductory level how to create models, how to perform exhaustive search, how to write specifications in a formal specification language, and how to deal with the computational complexity. So usually I teach it in like 16 lectures, full-blown graduate level class, and even you can just, for this particular subject, you can have a class of 15, 16 lectures. I won't be able to go in all the details, but I think it should give you still an idea how it works. So if you have any questions, I can always give you a reference to good books or papers so you can learn more. Or you can come and work with us, and then you will definitely become expert in this technology. Okay, so this technology called model checking is a relatively new area of research. It's been invented in early 80s by two independent groups, one in France and one in the United States. As usually, it's possible that two groups come up with similar ideas, more or less at the same time. And these people received the Turing Award in 2000 and... who knows? So it's 2010. I think they received it just a year ago, 2008, right? So Ed Clark, Alan Emerson, and Joseph Sifakis received the Turing Award for inventing a technology called model checking, but not only for inventing, but also for making it practical. So what's very outstanding about this work is that not only they came up with an idea, but they made it practical. So a lot of companies, both hardware and software industry, are using this technology as in their product groups. And this is really outstanding. In such a short period, within 25 years, you not only come up with theoretical result, but you really push it forward to be used by other people. And the idea, in a nutshell, is represented by this simple formula. If you have a system model, sometimes it's called implementation, and you have a system property or specification, you simply show up a satisfaction relation between the model and the system property. And you do it in a fully automated and fully mathematical manner. So this satisfaction relation or implementation or refinement relation is essentially the algorithm of which implements a particular graph traversal. Depending on a model you're using and depending on the property you're using, you might have different algorithms. So there is a whole bunch of different techniques which exist in this area of model checking, and putting it all together substitutes the area of research we are all working on. So naturally the model is more detailed and system specification is more abstract. So the model is all behaviors of your system. The property is something concrete, one particular specification, and our job is just to relate these two. So let's start with the model. So what do we have to know in order to create a model of the system? So we need to think about our system, what it is exactly. Is it a communication protocol, or it's a program which manipulates on data? Is it focusing on the communication structure of the execution, or it's really data manipulation? Then is it a sequential program or it's concurrent program? Is there, what kind of concurrency we have if it's a concurrent program? Is it interleaving semantics, or it is synchronous, asynchronous interaction among the system processes? And then if it's, for example, synchronous, if it's clocked, or it's totally independent of speed of process execution, and so on. Based on these considerations about the system, you decide in which model to use. And we can use many models which already exist for ages in mathematics. So can you tell me some models which you probably know from courses in graph or compilers? Finite automata. So you could have DFA, NFA, deterministic finite automata, non-deterministic finite automata. So what is about these DFAs and NFAs? Are they good for what type of systems? Event-based, yes, because you have a lot of, your automata have labels on the transitions. But are they good to model Linux operating systems?
To some extent.
To what extent? Say it again?
Sequential chunks of code.
So if it's a sequential, so it's not good for concurrency, you say? Okay. Is it good to model memory?
Well, not concurrently.
So I have my Linux kernel, so it's just continuously interacting, right?
Well, wait. We had a course.
Okay, possible.
Kernels. Actually.
Was it good?
It was very good because the guys who write our OS 200 operating system, they use this method. It's from Unitask system. So automata is...
So if I have a system which continuously interacting, it's continuously running, it never stops. It creates processes, it kills processes, it just keeps running. Can I use a deterministic finite automata or non-deterministic finite automata to model this fact that I have a dynamic memory, that I have an infinite memory? Can I use a finite automata to model infinite memory? Yes?
You have to use abstraction.
If I am reducing my infinite system to finite model such that I have a finite memory, then I can use finite models to model them, right? But what if I have ongoing interaction and then I'm not able to abstract it into finite memory any longer? I cannot. I need a different model then. For example, which model I can use for infinite memory? How about push-down automata? Have you heard such a thing? Push-down automata. It has infinite access to memory. This is the different model which can help me to deal with this problem. And so on. You keep thinking about what problem you're dealing with. So sometimes it's true, you don't have to deal with concurrency at all, and maybe you just look at sequential part of it, and then your model is just a simple DFA. Right? But by the way, you can use automata also for concurrent systems. You can really define a composition operator on several automata which will model concurrency. So it's not a problem usually. So that's fine. Okay. So that's a set of considerations you're making. You really have to see, you have a single input, you have multiple inputs on your system, you have again, a lot of data manipulation or just control. So maybe if you have a lot of data manipulation, you need a special model which would be good to store large sets of data. So naturally, it's important to choose the best model you have whenever you're creating a model. But the most important with respect to model checking technology is that you would be able to translate this into a state transition graph. So it's essential for us to have a graph, because we are going to use graph traversal techniques to check, to formally prove that properties hold or properties are violated. So that is the most important. Okay, so essentially, in a very simple way of presenting it, we are interested in finite state machines. Okay, now why finite? Why it's so critical for me to have a finite graph?
Because it's house to search. It's stable to house to search.
For exhaustive search, I need to traverse all possible branches. I cannot traverse infinitely many branches. In fact, this is undecidable. What does it mean? The problem is undecidable. There is no an algorithm. It simply does not exist to solve the problem. So I have to make sure I am restricting my search, I am restricting my job to a set of decidable problems. For example, if I restrict myself to finite state models, therefore I am restricting myself, I am really dealing with decidable problems then. Okay, so in the finite state machines, I have a state transition behavior, right? So I have a graph, I have nodes, and I have transitions between the nodes. And the transitions essentially depict the observable behavior of my system. My system is executing some particular functionality, and the transition exactly captures this fact. Something is happening, right? The behavior, the execution is captured by these transitions. So, for example, this is lock-unlock like a sort of mechanism. And I have 3 nodes, I have 3 states, and some of them are green and one of them is red. And the red is labeled as the bad state, is an error state. So the transitions, they show just a sequence of actions, like lock and unlock. And clearly it can be said that it's a good behavior when locks and unlocks are alternated. And if they are not alternated, then it gives you wrong behavior. For example, if I have lock, one after another, lock, it means it's an error, right? But if I have lock, unlock, this is a good behavior. And the same is I just have unlock directly and never get into locking situation anymore. So this is a specification just showing me good and bad behaviors. And this is a finite state machine. I have a finite set of states, right? 3 states, and I have a finite set of transitions. Do I have a finite set of behaviors? No. Why? This is the beauty of this model, right? In fact, I have a finite state system, but I am able to represent infinite behaviors by loops. If I have a loop, I still would be able to model something going on forever. This is very good because I don't want to have my model too simplistic, right? It has to be such that I am able to test it, I am able to traverse it, so I need an algorithm which would be able to do it. Therefore, I need a finite set of states. But I need to model my realistic systems such as recursive calls, such as loops in my program, and so on. Okay. Here's the example for a Linux kernel written in C. How I would be able to model. So my job would be to create a finite state machine. So for this model, then I would be able to verify some specification, which is also written, for example, as a finite state machine to see the kernel executes properly. So for this conformance check, I need to create this finite state model, which represents all possible behaviors of the Linux kernel. Okay, so meaning that I have two parts here. So the model checking part is where?
In between.
In between where?
In the second.
Yes, the model checking part is actually testing that the model satisfies the specification. But somebody already mentioned that I also need this step as well. Somehow I have to create this model. So if I would create it manually, that would be just too bad, right? Because what the whole point of this process of being fully automated? If I have to create it manually, I would make so many mistakes. There would be verifying something totally different from my actual program. So it's really essential that model is constructed automatically. So I need to have a technology which would allow me to capture the semantics of the program. It would extract the model such that it is the true model of the system. And then once that is done, I can do the formal testing here by doing graph traversal. Up to, I would say, 10 years ago, this part didn't exist. This part didn't exist. People, in fact, model checking by itself was created as follows. They were saying, let's suppose there exists a model somehow related to the software or hardware design, and let's say there exists a formal specification language to describe the specification, and then they define the set of algorithms which would perform this verification step. So it was wonderful and great, but totally impractical. And in fact, people were very skeptical, and they were saying, this never is going to be used anywhere. So the programmers, software engineers, they were saying, this is way too complex and nobody cares. They were saying it's theoretical result. But that's not the case any longer, and I'm very happy to tell you that these days, in 2010, we have tools which automatically create models from the system. Not only they create finite state models, they create very neat models, very compact models, which are really minimizing the state space representation of the system such that model checking step is not so expensive. So that is the case. Somebody mentioned SPIN, the model checking tool. So this is like really nice tool, one of the most popular tools. Though it still requires that you write your program, you write a model yourself in a language called Promela. So there is a special purpose language which is defined in order to create finite state models. It has nothing to do with the real products, right?
Well, actually, there were a model like
yes, it's another tool, exactly. So they are creating, but it has nothing to do with the same. And as far as I know, they are working on this task of trying to create it somehow automatically from C, but I haven't seen the product yet. Possibly it's coming, so I'm sure they are working on it. Okay.
How good these tools interact with pictures which they put on our source code?
You mean are they?
We are able to translate all Linux kernel to finite state machines.
Finite state machines, yes, can be created from a Linux kernel. So there are tools, I can tell you the names of those. For example, SAT-based predicate abstraction. So it's a tool from Carnegie Mellon University, from Oxford University, and from University of Lugano, which takes full ANSYS standard and extracts a model from any random C program.
Is it possible to find this tool from your page?
Yes.
So this tool is not a dynamic model building, but it's just build the model based on the source code of the system.
Yes, it's a static analysis, exactly. So it requires source code. It requires the system be already written, done. It's not running it. It's not done at runtime. But there are projects which doing it dynamically as well. So from constructing models from bytecode dynamically while running. So I'm not an expert in that area. So, but yes, there is a whole group of people working in this direction as well. Okay, so state transition graph. Let's go into a little bit of formalities and technicalities just to make sure you understand how we are able to do the verification step and how we are able to specify system properties. So this is the definition, formal definition of a Kripke structure. Kripke structure is essentially the finite state machine. It's a state transition graph which has a set of states. Some of these states are initial, and then it has also a set of atomic observations. So atomic observations correspond to data valuations. So if you have a variable which gets assigned to 100, this is a particular atomic observation. At some point in time, the value of x is 100. So I'm observing this fact and I want to remember it. How I'm able to remember it? I'm able to label the states of the system with these atomic propositions. Why do I have a power set operation here? 2 to the power of p. Because I'm labeling all states of my system with all possible atomic observations. My variable x could be defined as the integer. It might get assigned many different values, many different data parameters. Therefore, I have to able to label all possible valuations to the states of the system. And the transition relation is the Cartesian product of the states, right? Transition relation is a subset of the Cartesian product. Here is the very simple example. Kripke structure. I have 3 states, Q1, Q2, Q3, and states are labeled with observations A and B. When I'm labeling a state with label A, it means it's true in this state. So it's a Boolean label, right? A is either true or false. What does A represent? It is an atomic proposition, some particular atomic proposition, which, for example, can correspond to the fact that variable x gets assigned to 100. So whenever I'm saying A is true, A is equal to 1, it means x is equal to 100. And whenever I'm saying not true, it means x is not equal to 100. That's how I can remember how data changes during the execution of the system. And B is just yet another atomic proposition, some other proposition, which corresponds, let's say, Z is equal to 0, and so on. And essentially, I'm going to use this notation to describe sequences, to describe behaviors of my system. So the behavior is essentially a state sequence. So if I only care about how control changes, I can remember only a sequence of states. I'm calling them runs. For example, Q1, Q3, Q1, Q3 is a possible run on the execution of my system. But if I care about data, particular data, during the execution of the program, then I'm going to care about the sequence in terms of the atomic propositions, in terms of the observations. A, B, A, B, A. So why I'm just making it so difficult? Why I'm describing my system in terms of runs and traces? What's my ultimate goal?
Find the counterexample,
which will correspond to a particular execution of the system whenever I have a violation. My job is to encapsulate all possible behaviors of my system, right? And these behaviors are going to be represented in terms of different traces. A language, which is the union of all possible traces, defines the semantics of my program. All behaviors of my system, it means it's all possible traces of my system. So what I'm doing, I'm simply having a product. I have a Verilog program describing how this chip executes its own functionality. So I'm simply encoding all possible traces for Verilog program and taking a union of all of these traces. I'm defining a language of my chip. And this language I'm going to use it for graph traversal. So if I have an automata as a model, each automata has a language associated with it, right? So I can perform a lot of different operations on the automata using language operations, which will help me to formally prove something about the system. Yes?
From the first sample, we have two arrows, to the left and to the right. Does it mean that we have some hidden factor somewhere there? Because our program can't go both ways. It's deterministic. Am I right? Or we have some probability on transitions. That we can go to the state Q2 and to the state Q3.
Okay. Yes. So this is shows you non-deterministic possibilities, right? So I can non-deterministically go from state Q1 either to Q2 or to Q3.
Depending on some random variable.
Non-deterministic. Yes. Sometimes I need this non-determinism. For example, when I model concurrency, right? This is exactly a way of modeling concurrent execution. Okay, so having a state transition graph, what usually we do, we create what is called an infinite computation tree. It's essentially unfolding, unwinding of the state graph such that I don't have loops any longer. So having this explicit set of traces will help me to define the language of the system. So essentially a trace is an infinite sequence of state observations. Even though I have a finite state machine to present the system behavior, I'm able to to encapsulate infinite behaviors. Therefore it's really quite realistic. So realistic systems could be modeled this way. So, as I said, the semantics, therefore, is defined by a set of traces. So what is semantics? What does it mean?
Meaning.
A meaning, right. So whatever my program does, the meaning of what it's supposed to do is going to be defined by language of the state machine. Okay. Yes, again, Linux kernel. I do need to extract this model automatically. And this is quite non-trivial task. I have recursion, I have very complex data structures there. I have pointers, dynamic memory allocations. It's a concurrent system. I have many processes and many threads being created and being deleted. And it's a very large size. It's more than 1 million lines of code. Not easy, but possible. So, for example, our tools, we are experimenting with Linux kernel. We're taking parts of it, of course. We're not taking all the millions of lines of code. We take pieces and focus on particular chunks of the code. But yet people are experimenting with this these days. And these tools exist. This extraction, automatic extraction, is much easier for hardware. Why? Than for software. No, the model is the same.
Well, for example, we don't have pointers, so there is no pointer LS in software. So the model is simple.
Yeah, just the product is simpler by itself. Hardware designs, they only operate on Boolean variables, for example. And software can use variables like integers, infinite domains, right? So it's immediately becomes a problem, right? Of course, you constrain it within the limits of your computer. It's a finite, but still very large number, integer, right? Or float, or double, or character. So compare it to hardware, which operates only on Boolean variables. This is tremendously different. And yes, and just functionality-wise, so there are so many complex data structures in software, it just becomes a nightmare. Sometimes people do PhD research on figuring out how to model properly one particular data structure. So it could be quite a challenge. So dynamic memory allocation, creating of classes. So this is very difficult. But that's what people are doing, and that's what a lot of research groups are working on. Microsoft Research is very active in this area. They're doing an excellent job there. And then universities like Berkeley, Stanford, Carnegie Mellon, and many others, they have large groups working on these topics. So these days, everybody is doing it because it's still an open area. It's still an area where a lot could be done, and that's exactly what I'm working on as well. So for the reason that it's so challenging, it's so non-trivial and so difficult, and furthermore there is so much to do, then I really love it. So, and I'm inviting someone to join me there. So it's nice. So okay, let me give you an example how the model could be created. Here's some small program, and it's like simplified version of a mutual exclusion protocol. I have two processes, P1 and P2, running in parallel. So they are looping, and they are sharing variable last, right? And they also share
Looks like they share all three variables.
Are they sharing x1 and x2? Yes, they are. No, wait a second. This one cannot modify the x1, and this one cannot modify x2. It's reading it, but it's not writing. So, but they are modifying variable last, right? Both of them. So there is a shared data there. So anyway, so this is mutual exclusion that we have. They're both looping. They're running concurrently. So we have three control points: out, request, and in. So how would the model of which would encapsulate it would look like? So this is part of it. So I have 5 variables. Program counter of first process, program counter second process, and they have domain of 3 values: output, request, and input. And then variable x1 and x2 are Boolean, and there is a variable last, which could be 1 or 2. So, and that's how I start creating the overall state machine. So first state, which should be initial, on the top, it says I start at the point, for example, where program counter 1 is equal to out, program counter 2 is equal to out, x1 is 0, x2 is 0, variable last is equal to 1. And how I'm just describing what's happening to my system. It's just, for example, on this transition here, you see where I'm pointing? So what changed? Program counter 1 changed to request, and x1 changed to 1, right? The rest remains the same, and so on. For all possible changes of data, I am creating a new state. Remember the definition of a finite state machine? So this is my state, and this is my atomic observation. This is my label, which labels a concrete data value. So how many states I am creating for 5 variables, each of which has a finite domain, very small finite domain. I am creating 72 states. This is just the product of all possible values. Remember, my target is to create a model which would define exhaustively all possible combinations, all possible possibilities how the program could work. So therefore, I need to create a very large system. but that is perfectly possible. So I have 72 states for a program like this. 3 lines of code, 2 processes are in parallel. Okay, it means what I'm getting you to, that we do have a problem with state space explosion. It blows up. Blows up with the number of variables I'm using, and it blows up with the number of concurrent processes I'm having. So therefore, this technology it's essential that you fight this problem. You fight the state space explosion somehow. I will show you some techniques to do it, but later. Okay, let's move on. So we're realizing now how to model a system. Are there questions about it? There are many, of course, details there. How exactly? So, but in a high level, that's what you should get. Are you convinced that I'm able to represent a program using a finite state machine?
I have no idea how to deal with programs full of non-Boolean variables. For example, what can you do with integer variables?
It's a good question, yes. First of all, you have to going from in infinite, from minus infinity to plus infinity. First of all, you have to bound it somehow, right? Make it finite. So, for example, what would be a good guess to bound it?
64 bits.
64 bits, exactly. Just with respect to your processor machine, somehow you can restrict it to, something which you know about the architectural constraints of your system. So that's one of making it finite. But still it could be a very large number. So therefore maybe you can even reduce it further somehow to even a smaller domain. Now you might know something about the execution of your program. So you can remove what you don't care about and leave only a domain which is relevant to verification of your specifications. And this could be done automatically, and this I'm going to mention later. It's called abstraction. I'm abstracting away what is irrelevant to verification, and I'm keeping only what is relevant. So, okay, let's move on. So, and look at the other part, which supposedly is orthogonal to the system model, the part of specifying formally system specifications. And again, I need to think about what type of question I am asking, what exactly I am making up whenever I'm specifying a system. So, do I create a property which is operational or it's declarative? So if it's operational, possibly I would use automata to create the specification. This lock-unlock example I had before, it was example of a property. Property when I was trying to check that lock is always alternated with unlock. Remember, that was an example. So, and I used an automaton to capture it. Or maybe it's just declarative statement. Declarative like, whenever there are clouds in St. Petersburg, it means it will rain eventually. This is a declarative statement, and I might use propositional logic to describe this system. So maybe I can have a logical formula to do it. So, and then I could have properties which may happen, possibly happen, or which must happen. And then it means, in terms of formal specification, it means I have options, right? One way or another. So I can have a tree of possibilities to describe a system. So I can have branching specification of the system. Or something must happen. Must happen, it means there are no options. It must happen for sure. It means I would have a linear time specification. And another way to look at it is just to talk about, am I going to talk about bad or good behaviors? Bad means I don't want bad things happen. And sometimes we call these types of properties safety properties. And when I'm talking about something what good is going, I want something good to happen, eventually, sometime in the future, then we talk about Leibniz properties. So those are different classes. And again, it's important to think about it before you start writing a formula down. So you need to choose again modeling, the formalism, the specification language to make the better job of specifying the property. So I'm going to focus on one particular one, which is called linear temporal logic, for a number of reasons. First of all, it's probably the easiest to explain, and secondly, it's very natural. So because we humans are thinking just like linear temporal logic exists. So it's very intuitive to describe. Okay, so remember when I talked about models, I said that I remember some atomic propositions, the properties of states. These atomic propositions were values of program variables. So I'm going to reuse this notation, atomic propositions, to write property formulas now. Why? Because if I have the same set of atomic propositions, it will be easier for me to do the verification, to compare formula property against the model. And I'm going to talk in terms of traces. Traces which use atomic propositions as part of this specification. Again, the trace is just something very logical to write for a human being. Okay, here are two examples, which are, by the way, safety and liveness. So safety, something bad does not happen. So for example, mutual exclusion. No two processes can be at the critical section at the same time. This is a safety property. And then liveness. Something good will happen. I don't know when, but it will. So in terms of mutual exclusion protocol, so the absence of starvation, every request will be eventually granted. We can write these properties using the formal specification language called linear temporal logic, invented in 1977 by Amir Knoeli. And it's a logic which is based on propositional logic, allowing us to write formulas in terms of temporal sequences. So it's linear. Linear means I don't have options. Everything must follow in a fully deterministic manner. And I'm going to use sequence of states, and each state is going to be annotated with some propositional logic variable. This propositional logic variable is going to be exactly the atomic proposition which I'm using in my models. Okay, let's look at the very first. So it says next alpha. Next is a temporal operator telling me that in the next state something is true. For example, if I have a state here which is an initial state, then the next state after the initial state is a state which is gray. This is where Boolean variable alpha is true. Again, alpha could be just yet another variable y being 5. That's what it is. It says that in the next state, starting from the initial state, variable y is 5. And after that, for example, in this example, it's not true anymore. It's not gray. It's a different one. It means not alpha. First it's alpha, and then it is a negation of alpha. Is it clear what I'm doing? I have traces, and I'm annotating these traces with atomic propositions which correspond to my system. And I am able to reason in terms of time, like next state, eventually, sometime in the future, always, for all states, or I can even relate several propositional variables. For example, alpha and beta. Alpha is true until beta is true. So it's not a concrete timing, right? Not like I'm really tracking time. That's why it's not called timed specification. It's called temporal specification. Indirectly, I am able to reason about future, about past, about always, but I'm not able to reason about time explicitly. Why? Because if I start reasoning about time explicitly, it becomes extremely difficult, because I have to encode time as a separate state. And time, unfortunately, infinite, and it has a very large domain, the infinite one. So it means my system specification would just blow up on me. So I'm trying to avoid reasoning about time directly by this indirect meaning of temporal sequences. Sometimes it's enough, right? For example, every request is going to be granted. I don't know when it's going to be granted. If it's going to grant it in 5 minutes or in 5 hours, all I want to know is that it's not lost. It's my communication protocol. It's good enough. Maybe it's not very precise, but if I do it this way, I am decidable. I can have an algorithm to verify it. If I would have it explicitly modeled, it's undecidable. Okay, here are some examples. It's my personal PhD thesis I've done with NASA robot. This is a picture of the robot I was playing with when I was a student. So it has 17 degrees of freedom. So it has a torso and 2 arms, and it's highly concurrent, meaning that the
70 or 17?
17. So it has arms which can run in parallel, right? So there are many controllers on each joint of the robot, and NASA was very interested to make sure it never does something bad, such that they don't want it to destroy itself, and it definitely can, right? So the examples was that they don't want arms to cross, to hit the floor, to hit any other surface. So they don't want the things happen such that joints get bent in a direction when it's not supposed to go, so wires get broken and so on. So there are many hardware issues they were interested in, but since there was a computer in each joint, so they wanted to make sure the software which is embedded in this controller was doing well. So they gave us declarative statements about what they expect to happen and what they expect not to happen. And this is examples of those statements. The simplest one probably is the last one. Eventually the robot control terminates. And how I can always say it? I can say eventually, always, eventually, sometime in the future, and starting from this point in the future, it's always the case that this variable gets assigned to 1. So, and this is exactly the variable which the model of the robot using. So I would be traversing the model of the robot looking if that is happening, so that the robot terminates. Or with respect to the last joint of the robot arm, it says, if an instance of an end effector resides in the following design trajectory state, so there was like an execution following some trajectory, then the instance of the arm class remains in the valid state. So it's just coordination of the way how NASA engineers code it up. When it boils down to the program specification, it was like it's always the case that this variable, when it's equal to 1, implies that this variable is equal to 1. So these are formal specification. These are properties written in a formal specification language. This is properties written in terms of the traces of the program, and these traces are in terms of manipulation on the data, atomic propositions. Okay, so essentially I showed you having a finite state machine, having a property, I would be able to compare one against another by graph traversal. So there are many different algorithms. So I'm giving you the simplest one, which is called invariant checking. If I don't have temporal operators and my property is written in terms of atomic propositions, for example, I want to know if x is equal to 0 and y is equal to 0. Something like this. It's a very simple property, alpha. Then I would be able to do it by simply running a depth first search or breadth first search, right? By exploring the graph of my system. So I start from an initial state and I'm doing exhaustive analysis, DFS to BFS, and in any state, whenever I'm just traversing my graph, right, starting from an initial state. So I starting from an initial state, I look at the first state I'm visiting and I'm checking if x is 0 and y is 0. If they're both 0, I'm good, I continue going. I'm checking this state, I'm checking x is 0, y is 0, good. And then I get to the state, for example, x is 1. So this is bad. I found the bug. This is a failure state. So I can remember it. So once I find that the property doesn't hold, I am saying that I terminate my traversal and I remember this path. This is going to be a counterexample which shows the violation of the property. What's interesting about it, if it would be 0 here, and supposedly this terminal state for this branch, I just traverse back, find the state in a branch which wasn't explored. I will continue until I reach all reachable states. My algorithm terminates only when all states have been visited, unless the property is violated. This is simple. But for this type of properties, can be done quite straightforwardly. For different formulas with different operators, next, future, until, always, each of them have a different algorithm. So it would be much more complicated. But for all of them, people devise algorithms. Okay. Any questions about the technology, about the model checking?
Is it always possible to eliminate circles?
It becomes an infinite path. You unroll it, unfold it. You mean in the programs how you yeah, loop unrolling is okay. The state of the art. Many people, many static tools, they do bounded loop unrolling. Bounded means they say it's within this bound, and they unroll it up to depth n. But it is imprecise, right? It's actually unsound, because you don't know anything about outside of the bound you're using. I have a paper, recent paper, 1 year, 2 years ago, which we came up with an algorithm which soundly creates, we call it symbolic abstraction, symbolic loop summary, which doesn't do loop unrolling, it doesn't bound the loop, it just creates, we call it symbolic transformer of the loop body, such that it's a finite, but it's not missing any behaviors. So it's just
like abstract interpretation.
Yes, it's using abstract interpretation knowledge. So it uses abstract domains representing the loop body, and then you're using these candidates from this abstract domain as a potential invariance representing your loop body. And then you check if it's a true invariant representing the loop body. And if it's true invariant, then you can use it to abstract it, to create a symbolic formula representing the loop execution without any bounds. But this symbolic formula is a bounded representation of your system.
And these can be implemented as a part of the model checking tool?
Yes, we have a tool which does it fully automatically. So you can create, you take a... Right, you have a program with loops and then you do symbolic transformation using these abstract transformers we have, and it creates a loop-free program, which is an abstract model of your system, which is finite, and it does not bound the loops at all.
So first you need the program, and then
we do it together, actually. While extracting the model, you do this loop transformation. Yes. Naturally, it's a very complicated task. You have to do pointer analysis, you know. I mean, all the it's another, yeah, but, you know, loops are very often, like the parameters of the loops are pointer, manipulation of the pointers. So it's actually really coupled. So it's non-trivial. Well, we have a library of abstract domains. We have like string manipulations, you know, going from one character to another character, end of the string, and so on and so on. So, in fact, one of the students who've been sitting here 2 years ago are joining us in July, and he will going to work on automatic invariant generation for this particular technique I'm talking about. So we, as I said, right now we have library of abstract domains, and we simply take one domain at a time and extract random invariants, and then we have to test if it's a true invariant or not. We call it candidate invariance, and we run a SAT solver to check if it's a true invariant or not, and we keep doing until we find the proper invariant. Yeah, of course. But eventually we find it, but it's just a very tedious job. So, and automatically do it. This is it's a very difficult problem, so it's non-trivial. I mean, we have ideas how to do it, but I mean, it's starting. Well, anyway, so it's like in mathematics, this loop invariant generation is a very active area of research. But in mathematics means that they deal with polynomials and they create invariants for polynomial functions. Yes, but when it comes to software, to real programs, you know, then not one-to-one match. You know, so, and we are trying to figure out how to use these mathematical results to project it down to real software. So, but there are techniques which allow you to extract invariants automatically from a set of equations, of polynomial equations. It just, you cannot represent your program with a set of polynomial equations. That's the problem. So, well, anyway, so that's one of the active areas. We are working on it. Okay, so did I answer your question about loops? Okay, other questions?
What about model on a silent system? What depends somehow the model this sequences and the ability to build a model.
Okay, so you say that if I have a piece of code which it could behave differently depending on the environment.
Some other third-party libraries.
I see, which we don't have source code. Yeah, it's very common naturally, right? So we're all using libraries and we don't have source code of those libraries. So we simply saying that the environment, the third-party product can do just about anything. So it complicates my life horribly because I have to encode such that my piece of code, you know, can be influenced in any possible way. So it means I have to encode all of them since I must be exhaustive. It really blows up the size of my system, but I don't have an alternative, unfortunately. Unless somebody gives me the library, but they usually don't. Yes?
But they have some contracts on their behavior.
If they do, that's wonderful, yes. Yes, then you can, just take this contract and use it as a certificate.
When you make a model, you can make part of it from your source code and
Yeah, I've heard that in theory it exists. Never seen it.
Code can be broken.
I never seen this in real life. No, really. I mean, we run a lot of benchmarks, a lot of real life benchmarks. I never seen a single contract. But I've heard that it's this is the way to do things. So, yeah, Microsoft, in fact, is pushing it very hard, right, with their new product, with new languages. They are trying to make it like a must thing to do. So it's part of the compilation process. But it's not the case yet. So. Okay. Yeah, by the way, just to mention, so we do work with Rustan Leno from Microsoft Research, who is working on this contract-based programming languages. So, and they have a tool called Boogie. So, and he keeps saying that he really wants to combine it with other techniques on like loop summarization, for example, and abstract interpretation. So, maybe if somebody is interested, feel free to come and talk to me about this area of research as well. So, but actually, I don't know where to start. It's not that trivial. Okay, what's time? What time? 6:17 my time, 8:17 your time.